I'm quite enjoying these, so I'm going to do another one. The next question in Sierpinski's book is that if n is a positive integer, then 169 divides that mess there. And this is the sort of thing that works by induction, right? And why have I got a blue unexpected end of comment block? Let's restart lean. So the proof will be by induction, right? Proof. I mean, let's just consider. So the base case. I mean, why does he restrict to positive? I mean, why don't we let n be 0? If n is 0, then we get 3 cubed. We get 27 minus 0 minus 20. So we get 169 divided. It's true if n is 0. What's he got against 0? So that would be the base case, and then the inductive step. Let's see if it works. Induction on n, base case n is 0 works fine. An inductive step. We just need to look at the difference, right? Let's look at 3 to the 3 times n plus 1 plus 3 minus 26 n plus 1 minus 27. And now I subtract 3 to the 3n plus 3 minus 26n minus 27 is what? So this is 3 to the 3n plus 3 plus 3. So it's 3 to the 3n plus... Oh, this is a bit annoying. 3 to the 3n plus 3 times 27, right? So... Ooh, maybe induction doesn't... Am I being crazy? Does induction not work? 169 is 13 squared. Ooh, I've been caught out. Do I just multiply this by 27? That would... And then I would get... what's 27 times 26? Oh, here's an interesting question. What's 27? Right. We know that 169 divides 3 to the 3n plus 3. So let's say we know 169 divides 3 to the 3n plus 3. Minus 26n minus 27. Then it divides... I'm going to multiply it by... If n goes up by 1, then 3n goes up by 3. So that thing goes up by 3, and 3 cubed is 27. Then it divides 27 times this, which is 3 to the 3n plus 1 plus 3, minus 26 times 27 times n, minus 27 times 27. And we want it to divide 3 to the 3n plus 1 plus 3 minus 26n, or minus 26n plus 1 minus 27. So we're done if it divides the difference, which is... And if it doesn't divide the difference, the question's wrong, right? So it's 26 times... Which way am I taking away? Which is biggest? I think this one is biggest. So it's minus 26n, minus 26, minus 27. And now I want to add 26 times 27n. And I want to add 27 times 27, which is... Is this going to work? Oh, yes, it is going to work. Oh, that's good. Because it's 26 times 27n minus 26 times 1n. So it's 26 times 26n. Ha ha ha. Great. Add 27 times 26. No. Yes. minus 27, which is 27 times 27 minus 27 is 27 times 26, and then I minus 26 and I get 26 times 26, which is 13 times something. Okay, great. Right, after that rather bumpy start, we've got the maths proof. So, example, I claim, so n is a natural number, and we've got this hypothesis on n, is that n 0 is less than n, which we're not going to use. Remark, not going to use it. And the conclusion is, we're not going to use hn. And the conclusion is that 169, so I'm going to work in integers, right? Because if I wrote this for naturals, then it literally would not be the statement, because natural subtraction is not, that subtraction there is not natural subtraction. So it's 3 to the power of 3 times n plus 3. Oh, is that going to work? Yeah. 3 times n plus 3. Minus 26 times n minus 27. And bingo. And I am claiming, I'm a bit worried about, am I? No, there you go. There's the, right, great. So we can see that this is an integer. We've got that little up arrow there. And I'm going to do it by induction. Induction n with DHD. And the base case should be norm num, hopefully it is, and the inductive step. Have we got? Do you know what? I'm gonna clear hn. I think it might be safest. Because now it's not there at all. So now how's this inductive step? I mean, maybe I could do this there, and then not bother indenting. So what was our strategy? So we've got d dot, I don't like d dot suck, so let me rewrite nat dot suck ec add 1 right away. Because when you use Lean's induction tactic, it uses the constructors, which is 0 and suck. So now what are we going to do? We're going to do, so this is going to be quite a struggle, I suspect. Well, maybe not a struggle, but still. The first thing we need to do is we need to multiply this first thing by 26. So we need to know if A divides B, then I claim A divides C times B. So what's that? So example, A, B, C, and Z. And then we've got the hypothesis that A divides B. And I claim that A divides C times B by library search. So that's bound to be in there somewhere. There it is. So let's have h colon equals dvud mul of dvud right, and then we want to apply that to hd, and then we want to do 3 cubed. I mean, it's 27, but let me do 3 cubed. And it doesn't. Oh, what have I done? Oh, was it an issue 3? The integer 3 cubed, was it that? Yeah, okay, great. So now we know that there, and that's that times that. So now we need to work on this hypothesis h, right? So now we need to turn this into 3 to the 3d plus 1. I'm not sure ring will do that. It doesn't look too difficult to do manually though. So rewrite. First thing I want to do is take the thing out of the brackets, right? So that's rewrite mul sub. Rewrite mul sub at h. And now I've got 3 cubed times 3 to the something. So now I want to do pow. What do I want to do? Pow add or something. I'm just sort of guessing what these are called. Oh, no, I haven't got it out yet. I need to do another mul sub. That's interesting. Mul sub. How about that? Bingo. So now I've got 3 cubed times 3. I'm trying to turn this thing here into this thing here, because I think that it will somehow be easier to use. And now this is x to the a times x to the b is x to the a plus b. What will that be called? I don't know, pow add. There is a pow add, and indeed it is pow add, but it looks like it's the other way. So I should rewrite left pow add there. And now I've got 3 plus 3 times d plus 3. Well, this is very close, right? Do I want to keep working on this? I suppose I could I could just rewrite mullad at the goal, couldn't I? And now I've got 3 times d. Oh, come on. And then rewrite mul1. Let's get rid of this. And then add column, I guess. How are we doing? Right, they're great, they're the same. Super. And now the trick is, yeah, so it suffices. So now I should figure out what's going on. So it suffices, I claim it suffices that 169, the integer 169, divides, and it's something like this thing here, minus 26 times n, whatever, blah, blah, blah. And did I put the wrong divides? Yes, I did. So, oh, and I haven't got an n, 26 times d. So that's not right, but we'll get to that in a minute. So suffices, what should we call that? H2. I'm going to change the right hand side, and then I want to do something like convert. So the idea is that this is going to be, if I add h and h2, I'm going to get exactly this object here. So so convert, what was that called? Divide add h2. Oh, why have I got 2 goals? Oh, I see. Suffices this. I could put a sorry here. Oh, what about, okay, let's put have. There, and now I've got to prove something that probably isn't true, because I just guessed. I guessed what this thing was here. So now the question is, I mean, I could put 0. And now the question is, what should I be putting here instead of 0 that's going to make things work? And so now those things are going to cancel there. I mean, I want to get, can I get ring to do this? Oh, the things didn't, why aren't those things cancelling? Ring neuf, will that do it? They're not going to, why are they not cancelling? Simp? Right, okay, I'm going back to my computer algebra package. Because Liam was not cut out to do, things like this. So, there, the question is, what should that 0 actually say? And the idea is, I'm going to put everything on the left hand side, so those will cancel. So it's 3 cubed times 26 times d, add 3 cubed times 27, and then I want to minus 26 times d plus 1, and I want to minus 27. So it's 676d plus 676, so 676 times d plus 676. And that doesn't look too difficult to prove, right? Because 676 will be 4 times 169. So I could put 169 times 4 times d plus 1. No. Yeah, 4 times d plus 4. There. And the proof of that we can probably do because we just, in fact, that will be in the library because it's 169 times something. So there we go. And so now how are we doing? And now, oh, now ring doesn't do this. Oh, that's a blow. Oh, yeah. Why does ring not do this? Is this wrong? Oh, maybe. Oh, there's ring X. Is it because of the exponent? What? Oh, it's because of the up arrow D plus 1. Lean doesn't know the up arrow D plus 1. Okay, I think what's happening is that D is a natural, and D plus 1, that's taking place in the naturals, and then we're coercing that to the integers. And what we need to be doing is we need to make that say up arrow D plus 1. And the way to do that is push cast, right? Yeah, there we go, I've done it. Okay, problem solved. So let me just, so that's kind of, let me explain about norm cast and push cast now we're here. So what's going on with norm cast and push cast? So this is forever this problem that D's a natural number, but we're proving a goal with subtraction in, so we really need to use integers, because, you know, if I wrote that as a natural number goal, it sort of literally wouldn't be the same. It wouldn't be the same assertion in some sense. So we have to write the goal. You know, if we want to literally translate the question into lean, we have to use integers. And what's happening is that there's this sort of slight annoyance that D plus 1 is a natural, and so this up arrow D plus 1. So there are these tactics. You see, the idea is the point is I want to check that the obvious map from the naturals to the integers is an additive monoid homomorphism, right? I want to check that up arrow D plus 1 is up arrow D plus up arrow 1, and that up arrow 1 is 1, that sort of thing. So you can imagine doing everything from first principles would be a nightmare. But we have these norm cast and push cast. Norm cast tries to pull arrows. You see, now I've got arrows right at the front of everything. Lean is like, yeah, we can, D plus 1, that's an integer. We can, that's a natural. We can multiply it by 26, that's a natural. And then we can coerce the whole thing to integers. So normcast tries to pull the arrows out as far as they can go. You see, the reason they won't go any further is because of these subtractions. You see, it's not true. It's not true that right. Look at this. Like this. I've shown you this before, right? Eval the natural number 2 minus the natural number 3 is 0, right? This subtraction on the naturals is not mathematical subtraction. It's a sort of a pathological function invented by computer scientists. And so it's not true that up arrow A minus B is up arrow A minus up arrow B. So what normcast does is it tries to pull the arrows out as far as it will go, but it won't pull them any further than the subtraction. And pushcast does the opposite. That's a lot of fun. There we go. Pushcast has, for some reason, changed a whole lot of 26s into 1s. But there we go. Let's pretend that never happened. But pushcast pushes them in as far as they'll go. So you see now we just have up arrow D. And then we've got an up arrow. You see now everything is up arrow D. And the only thing that's a D is in the exponent. And that's correct, right? Because we're not taking 3, we're working in the integers, so we're taking things to the power of a natural number. Here that D needs to be natural, right? We can't take 3 to the power negative 1. If we were doing that, then it wouldn't make sense to start talking about congruences, because we'd have left the world of integers. So there you go, that's something about pushcast and normcast, and there's a relatively short proof of Sierpinski question 4. Thanks for watching.